Good evening, students. In previous class, we have discussed about expected questions from current electricity, and in this session, I am going to discuss about expected questions from moving charges and magnetism. Let us start the session. Moving charges and magnetism. Here the first question. A closely wound solenoid 80 centimeter long has 5 layers of winding of 400 turns each. Look at the figure. So here a closely wound solenoid whose length is 80 centimeter long. It has 5 layers, okay, of winding of 400 turns each. Okay, it has 400 turns. The diameter of the solenoid is 1.8 centimeter. So its diameter is 1.8 centimeter. If the current carried is 8 ampere, estimate the magnitude of magnetic field inside the solenoid near its center. So we have to find magnitude of magnetic field when current 8 ampere is flowing through this solenoid. Okay. Solution. Number of turns per unit length. See, first we have to find number of turns per unit length, that is small n. That is small n is equal to total number of turns into number of layers by total length. That is equal to total number of turns 400 into number of layers 5 by length. Length of solenoid is given 80 centimeter, so we can convert into meter, means 0.8 meter. Then if we simplify, then we will get 2500 meter power minus 1. So we got number of turns per unit length. Now magnetic field inside the solenoid, that is B is equal to mu naught Ni, where mu naught means magnetic permeability of free space, N means number of turns per unit length, I means current. So that is equal to mu naught value 4 pi into 10 power minus 7. That is small n value we got 2500, okay, into I 8 ampere. So we substituted here. Then if we simplify, we will get 8 pi into 10 power minus 3. That is equal to 2.5 into 10 power minus 2 Tesla. So we got magnitude of magnetic field inside the solenoid. That is 2.5 into 10 power minus 2 Tesla. Now we will go with second question. Here the second question. Two long and parallel straight wires A and B carrying currents of 8 ampere and 5 ampere in the same direction are separated by a distance of 4 centimeter. Look at the figure. So here two long and parallel straight wires A and B carrying current I1 I2, that is I1 is 8 ampere, I2 is 5 ampere, and they are separated by a distance r, that r given 4 centimeter. So we have to calculate the force on a 10 centimeter section of wire A is. So we have to calculate here force on 10 centimeter section of wire A. Okay. Solution. Force per unit length, that is F by L is equal to mu naught I1 I2 by 2 pi r. That is equal to mu naught value 4 pi into 10 power minus 7, I1 given 8 ampere, I2 given 5 ampere, by 2 pi into r 4 centimeter, so 4 into 10 power minus 2 meter. So if we simplify, we will get 2 into 10 power minus 4 Newton meter power minus 1. Now we have to calculate force here. So force is equal to this L, we have to move to the right side. So if we move L to the right side, then we will get force is equal to 2 into 10 power minus 4 into L. So here 2 into 10 power minus 4, okay, into L here 10 centimeter. So that is 10 into 10 power minus 2 meter. That is equal to, if we simplify, means we will get 2 into 10 power minus 5 Newton. Okay. Next we will go with third question. A square coil of the side 10 centimeter consists of 20 turns and carries a current of 12 ampere. The coil is suspended vertically and normal to the plane of the coil and makes an angle of 30 degrees with the direction of uniform horizontal magnetic field of magnitude 0.8 Tesla. What is the magnitude of torque experienced by the coil? Solution. So torque experienced by the coil, that is tau is equal to NIBA sin theta, where N means total number of turns, I means current, B means magnetic field, A means area of cross section of coil, sin theta. Okay, theta means angle between B and A. Okay. So in the place of N, I substitute 20 turns into I 12 ampere into B 0.8 Tesla into A area of cross section, that is it is a square whose side 10 centimeter. So side into side square, so 10 centimeter, 10 into 10 power minus 2 meter whole square into sin theta, 30 degrees, so sin 30. So if you simplify, we will get 16 into 12 into 10 power minus 2 into sin 30 means 1 by 2. That is equal to 0.96 Newton meter. So we got torque experienced by the coil, that is 0.96 Newton meter. Now we will go with fourth question. A horizontal overhead power line carries a current of 90 ampere in an east to west direction. What is the magnitude and direction of magnetic field due to the current 1.5 meter below the line? So we have to calculate magnitude of magnetic field and its direction due to horizontal overhead power line. Okay. Solution. Magnetic field due to infinite straight wire, that is B is equal to mu naught I by 2 pi r. So if you substitute mu naught means 4 pi into 10 power minus 7, I means 90 ampere by 2 pi into r 1.5, then we will get 1.2 into 10 power minus 5 Tesla. So we got magnitude of magnetic field due to infinite straight wire. Now we have to calculate direction. So what is the direction of the magnetic field? If we apply right hand thumb rule, then we can say the direction of magnetic field is towards south. So that is towards south. Okay. So that's about this session, my dear students. I hope you like this session. If you like it, please put like. Your likes gives more strength to do more videos. Okay. Please share it, subscribe it to your friends and relatives. These are very, very important questions for your upcoming physics board exam. Okay. Bye, students.